Stanford University.
Let me talk to you about LIFE, which is laser-initiated fusion energy, which is a path to sustainable carbon-free energy in our future. And what you're looking at is the National Ignition Facility, which is the world's most energetic laser by about a factor of 100. It's now operational across the bay. And, and it's something I'd just like to share some thoughts about you. I want you to know a lot of it came out of Stanford faculty and students, just to name a few, who played some role in it. I always like to point to Tony Siegman, you know, in the late 60s and early 70s, I read that was the first book I ever read about lasers. You know, Bob has played a tremendous role over the years, and this is just some of the students that came out of Stanford that work at the lab on high energy density science on the NIF. So there's a big posse over there that are a part of our team. And you know, we are always hoping that more students from here want to come over. And I hope after seeing this, you'll want to think about that. So the question that we're going to talk about is, could we build a miniature sun on the Earth? You know, when the NIF was first put together, that's sort of the fundamental question. There was three basic uses for the NIF: strategic security, and that was after President Bush, the first, you know, stopped nuclear testing. The question was, could you assure that nuclear weapons would work, you know, in perpetuity without ever testing them again? You have to get conditions, high energy density science conditions, which are millions of atmospheres up to several hundred million degrees and densities of 100 times that of lead. There was also the astrophysics in the laboratory. You know, could you create conditions in the center of the sun, supernova, neutron stars, and the like, Jovian planets of the like, you know, and do those kind of physics? And finally, there was the long pole in the tent. Could you get to fusion energy? Fusion energy was always tremendously interesting. Why? Because, you know, equals mc squared and H2O are kind of, you know, catchwords. You know, you're just burning hydrogen. There's a lot of hydrogen around. And you know, equals mc squared, a small amount of mass converts into a huge amount of energy. And so this is the true solar energy. And could you make that true solar energy right here on Earth? Instead of harvesting photons, could you harvest neutrons, turn them into electrons? That was one of the big questions. Well, it seems that we are sort of on the verge of being able to do that. It's been a long battle, as Bob just said. In fact, it's now 49 years into this battle. And it actually wasn't a year, just to tell you. It was actually about a day and a half. You know, after Ted Mayman demonstrated the laser at Hughes Aircraft in Malibu, about a day and a half later, John Knuckles and his team, you know, who were thinking about, you know, this problem anyway, went, you know, oh yeah, okay, we see that. Now that's when lasers really were just pretend, but they were conceptual ideas. And over the decades, we've put together one large laser after another. And finally, we're at a place where people are generally in agreement that the National Ignition Facility is the scale of laser that you need to actually do fusion. And by fusion, we have to be very careful. We mean fusion energy with gain. So more energy out from the nuclear reaction, you know, the fusion reaction, than you put laser energy in. There have been, over the last 3 decades, demonstration of fusion, but not with gain. Gain is the issue, right? So if you get more out than you put in, you may have an energy source. What's great about it, this energy is limitless fuel, right? It's carbon-free. It's non-proliferant. It's non-geopolitical. It's almost better than you could imagine. But it's been damn hard to get here. You know, the NIF is now operational. It's the largest scientific construction project successfully completed by DOE. It's probably the largest project that's going on in the world today. And, you know, to give a scale, I don't know, you know, it depends on where I am in the Bay or in the California. Really, it's only the Cardinals here. Anyway, so that's the scale of the laser. So even though we don't play football on the roof, that is the scale of it. So it's sort of like a Kia size, right? And you know, this is an interesting problem in its own right. We have ideas to make it much smaller in the future, but it's this big because it's an extremely flexible facility to meet a lot of different missions. And the main idea of NIF is to, with the I in ignition is thermonuclear burn, it's propagating burn, is to get matter temperatures of 10 to the 8th K, radiation pressures over 300 eV, densities of 100 times that of lead, pressures of 100 billion atmospheres for fairly short times. Like in this case, we talk about assembling a target in 20 nanoseconds, getting burned for 10 picoseconds. So I don't know everyone in this audience, but you know, 10 picoseconds is not a millionth, it's a billionth. So you know, it's 100 billionth of a second. So it burns for trillionths of a second. But what's really interesting about that, it's the same as what's going on in the sun, except it's a little bit hotter, it's a little bit more pressure, and it doesn't take millions of years to get a fusion reaction to go. It takes picoseconds. So that's what drives us. And just let me just go back, and you can see that target, even though that's a big building, that's a small target. That's the full-scale target. And inside of that is where the hydrogen that we burn. By the way, we burn deuterium and tritium, which are isotopes of hydrogen. We use those too because they go at the lowest temperature, which is around 40 million degrees. They'll start burning. Once they start burning, believe it or not, it goes up to around 800 million degrees. So it gets pretty warm for a very short time. This is what the laser looks like, and I'll stop it for a second. This is through the miracle of CAD. You can see what the system looks like. I always have to use a screen laser. You know, Dr. Bayer invented this laser a long time ago. You know, as he's always pointed out, he invented it too early. You know, so by the time it became commercially acceptable, you know, all the patents had run out. But this is an important device. And this over here is the target chamber. And these are the laser bays. There's 2 laser bays, which we very cleverly call laser bay 1 and laser bay 2. And what you're going to see here is that we have beams going back and forth here. They start here. We have a gain of around 10 to the 15th in this system. So you start out at nanojoules and go out to megajoules. So it's kind of an interesting laser. So this, let me try that again. So this is what happens. We start out with a very small energy laser, put it out into the bays, go up in 192 beams. Each one of these beams are the highest energy lasers in the world. Every single one. We go from 2D to 3D, 3D to radial, and then we hit those targets. And that's where you learn that you get those neutrons out, and that's where you learn that neutrons are yellow. So this is the facility. So this facility takes about, between the time you set up a shot, fire the laser, and the time it's shot, the laser beams get to the target is 1/millionth of a second, it's a microsecond. It takes about 20 nanoseconds to assemble a target, so the beams are around 20 feet long, and you get burned for around 10 picoseconds. So it's hardly ever on, right? So, but you get a lot of interesting things going on. This is what a laser bay looks like when it's finished. So if you come over to the lab, and I hope you all find some time to do that because we'd love to show you the place. This is a laser bay. It's around 400 feet long, or if you're in the metric world, it's a little bit over 100 meters long. And each one of those pipes is where the laser beams travel. So this is one, and there's 48 in here. It's 4 deep, 48 here. This is one of the laser bays. The other laser bay has the other 96 beams. Again, these are infrared lasers. They're neodymium lasers, and we have to turn the light to ultraviolet before we go into the target, which I'll show you. So on March 10th, which is fairly recently, this became the first megajoule laser facility. This is the target bay. It's kind of an interesting looking device, and when you see it, you'll find it very interesting. And these are where the beams come in from the top. We also have a mirror image coming in from the bottom. And 1 megajoule is a nice number for a couple of reasons. First of all, it's around 40 times more than anyone has ever done before much more importantly, this is the energy you need to get burn, we think. So this is the first burn-capable laser that's ever been built. You know, right now, we're getting ready to start our experiments. Actually, this summer, we'll be doing the first experiments to test ignition. Now, there's always the joke that, you know, in the fusion community, that fusion is 50 years away, no matter what year you ask. In fact, what day you ask, what decade you ask. And I think this is what I want to talk about the rest of this talk is, you know, and we're going to deal with it. We don't think it's 50 years away anymore. In fact, we think we'll get burn in the NIF in the next 2 to 4 years, depending on, you know, your confidence in actually, you know, certain parts of the physics coming together, and actually the issues of logistics of putting this all into an operating facility with respect to the diagnostics, cryogenics, and the like. But as far as the laser is concerned, you know, it meets every single spec in terms of its energy, its power, its pointing, timing, and they're very specific and demanding specs. This is not a flamethrower. It is the most precision laser of its kind ever built, also besides very high energy. That's what the inside of a target chamber looks like. There's two things that are interesting about this picture to me. First of all, the scale of the target chamber, which is 10 meters in diameter. Second of all, this picture, if you notice, this was taken by National Geographic, and you notice that everywhere in it, it's in focus. And so I thought the lens that this guy had was far more interesting than a lot of optics we have in NIF. So, but that's a normal sized American. He's around 6 feet tall. It gives you a scale of it. Where you see these square beams right here, you know, these round ports with the squares where he is, that's where the light comes in. These little round ones, and there's 108 of them, are for diagnostics. So we can have all kinds of diagnostics, optical diagnostics, X-ray diagnostics, and neutronic diagnostics. Can you guys hear this? This is a countdown. This is actually in the control room. This is real, but we're going to go to a cartoon for a second so you can see it. Okay, so that is a 20 nanosecond pulse. You know, light travels a foot in a nanosecond, in a billionth of a second. So this is going about 100 millionth speed. NIF actually plays music, you know, when it's going. So every time you see that purple glass is where you get the gain. So we're watching what's called the bundle, 8 beams heading towards the target chamber. And this is taking less than a millionth of a second. Now we're about to go into the switch yard that we showed, and we're now going to turn as we go to the target chamber, we're going to turn the light green and then blue, and then focus it on the target. Now remember, the target is about the size of a pencil eraser. And that little ball in the middle is where the frozen deuterium and tritium is. You can see the billionths of a second going all around. So as this is happening, this little gold capsule is a gold oven. It's going up to around 4 or 5 million degrees. It's radiating X-rays onto that target, which is plastic. It ablates it and drives the ice together at 1,000,000 miles an hour. And when it's about the diameter of your hair, you know, 100 microns, you have those conditions. And then you have fusion and it lights up, and for all of 10 picoseconds, it burns, right? So what's happening in that time? You're putting light in, you know, in the ultraviolet. You're making X-rays. Those X-rays are absorbed by the plastic shell that holds the DT. As it ablates, it's a rocket, right? It's a radial rocket. It drives, you know, Newton's laws. Every reaction has equal and opposite reaction. As that stuff ablates, the ice is driven in at about 1,000,000 miles an hour. And if you do it just right, you know, so it doesn't get unstable as it goes in, and it's around 10 to the 13th Gs. So think about that if you want to snap your head back, right? You know, it's 10 million Gs, right? It will go in, and when it gets about the size of the diameter of your hair, you have those conditions, 1,000 times that of lead, 100 million degrees. It starts burning, and it now bootstraps, goes alpha heating, and you get fusion burn. And you can burn around the quarter of the fuel. If you have a couple of milligrams in it, you can do the calculations. That c² number is pretty big. You can get out 40 megajoules. Now 40 megajoules in, 1 megajoule in from the laser, 40 megajoules out, you have a gain of 20 to 40. You're sort of in the game, right? It's kind of an interesting situation. Now, for people who aren't scientists, I know this is a very mixed group. People always wonder, is that sort of something wrong with that? You know, perpetual motion, things like that. You know, no, it isn't. It's, you know, remember, you know, there's a huge amount of energy to release stored in mass. And if we can find a way to do that, that's how you can get this to happen. The way the energy comes out is in X-rays. About 20%, 80% comes out in the kinetic energy of a neutron. If you could collect that energy as thermal energy and finally boil water or something like that, make steam, turn a turbine, you have electricity, you have electrons. What's great about these electrons, from here, if these were fusion-generated electrons, you couldn't tell that except when you went outside, because there would be no pollution and there'd be no carbon, right? And you wouldn't be worried about the Mideast anymore. You know, that's the nice part. That's the dream game. This is actually what it looks like. This isn't a cartoon anymore. So that's what the laser looks like when it fires. One shot, 3 views. I'm going to show you in slow motion. There is no information imparted. Just cool looking, right? So people wonder, why can you see light if it's a laser, right? Because remember, I will shoot this laser across the room, and you can only see it where it hits the wall, right? You can't see it in the air. Because it's all going in one direction. No light is going towards you. That's actually flash lamps. So what we do is store energy in capacitors. We charge them up. So electricity is stored in, you know, rechargeable batteries, actually. That's how we store energy. Then we discharge it into a flash lamp and make photons. And then this laser glass or optical batteries, they store that light energy as quantum states so that you can take it out later. So when you think of that laser, I think of it as an optical battery. And we can get out energy, you know, those beautiful photons. They go in the same direction, same color, and like they want. That's the target, as it looks like to a physicist. And it's a little bit more complicated when you actually do it. Now, I want to say something about NIF. Besides doing the Premier mission that we do, it's also going to, I know how to work this place now. Okay, it will also do, you know, Premier International Science. And remember, this is going to create conditions that exist nowhere else on Earth, but are very interesting all over the cosmos. You know, why does the Earth have the magnetic field it does? You know, the iron in the center of our Earth does not look like the iron here. You know, and the iron and the methane and hydrogen in Jupiter and Saturn look very different than we think they do. And we can do measurements that are exactly like that. We can also make suns, supernova, and I think I said this, even neutron star atmospheres. You know, and so what the thing is so great about this, you can take astrophysics from an observational science into an experimental science. So the idea would be you could, you know, schedule a tiny little supernova, you know, on June 18th at 3 in the afternoon. Bring your instruments, and you know, we'll do some experiments. So that's another thing we're going to do. But I want to go back to, you know, energy, because I know that's what you're mostly interested in at this moment. We believe that achieving ignition, thermonuclear burn with gain at the National Ignition Facility can be really a defining moment for the world's energy future. Now, I want to go back to that 50-year problem, right? You know, there is no policymakers in the world anywhere right now thinking about fusion as a part of their future. So if you go to the ITER facility in Cadarache, France, you know, which will have burn maybe in 2025, you know, and then it will be 2060 before it could be commercial. Actually, it's not a part of anyone's thinking. And what I want to say is that we think there is a way through this, and it could be done in the next decade. And my assertion is we believe if there's a will, there is a way. So we're talking about a laser inertial fusion-based approach for power generation. Now, I think you all are expert in this, so I'm not going to spend a lot of time on this, but clean energy may be humankind's challenge. Some people think it is the existential challenge. I'm not here to judge that, but many people do think that between population increase, a large portion of our planet's population is energy extremely poor, 1/10 or less of the energy that we use, resource depletion, climate change, pollution. These are huge issues that we face as a species, and this 50-year problem is an extremely uninteresting time horizon at least for me, in the context of this problem. So when you look at what's going on, we sort of see the world population going up by 3 billion people in the next 30 years. And so it's sort of going up like 100 million people a year, right? As people basically understand it. So that's in the every 3 years you get another United States, every 10 or 12 years you get another China. That's pretty scary. And they want energy, and they're using coal, right? Coal's a terrifying event. I don't know how many of you have been in a strip mine. I have been. And when you get down there and you realize that these trucks have wheels that are around 12 to 15 feet high, it sort of gives you a scale of what's going on. So what we do is we dig this junk out of the ground, we burn it, it goes up into the air, except for the stuff we just leave to pollute the water. So it's kind of a messy situation. Clean coal may be in our future, but it's a hard problem. It's a real hard problem to deal with. Here's a picture I took in Beijing. This is like LA in the 50s, 60s, some days even today. And the reason fusion energy is so interesting is because if you look at, a few hundred kilograms in a pickup truck of heavy water, that has an energy equivalent of 2,100 railroad cars, right? And what's good about that, again, it has no carbon in it. D2O does not have any carbon in it. And the problem is, when you look at all these ideas of how to deal with energy, whether it's population control, bicycles, biofuels, wind, water, solar, these are all, every single one of these problems is hard to scale up to, or they have huge social impacts. When you look at nuclear or fusion, the world is, the United States is 20% fusion, has been for a long time. Fission, I'm sorry, I'm dreaming. I was just flashing ahead there. So it's around 20% fission, has been for a long time, even though people don't realize that. Even though 3 Mile Island happened, there hasn't been a new reactor really put operational since then. The efficiency of those systems has gone up, and the availability, just at the rate that that amount of the percentage rise has stayed the same. So, but we can't seem to get going on fission. And the question is, could you do fusion? Okay, there are two major approaches for fusion. One is magnetic fusion. That was invented in the 50s by the Russians. And this is the ITER facility. And I just have to show this guy so we get the scale. This is the normal size European, right? Right there. So that is the target chamber for, MFE. It's a very low density machine. High temperature, low density, right? It takes a long time. The Wilson criterion, which is to measure this, is measured in very long periods of time, seconds, minutes. Whereas this is the NIF target, where our target, of course, is the size of a pencil eraser, right? And we hope to show our ignition gain in the next, starting next year. So challenges for fusion energy, though, is not that scientific part. Because even if we get that, what's the step after that? So even though we have a lot of confidence in that, could we make it available? What's wrong with fusion energy? The trouble is, The good part is it's high neutron yield, it's no greenhouse gases, very low levels of radioactive waste, and it's shallow ground burial, short life. But it's been very hard. Pure fusion solutions have been technologically very challenging. Why did we have to build that big laser? And economically even harder. We think we have some ideas that could change that. And the reason that we do think that is that life is a life engine, which is this laser initiation fusion energy, just looks like NIF. It has one little difference, if NIF works, which we hope it will. There's NIF, right? Just a little bit of art. We just put a balance of plant in. You have to turn the thermal energy into electrical energy. So you got to do that. In order to make electricity, you have to do that. So there's the place where you turn that into, that can be around a 40% process. For temperatures that are pretty low and capable, it might go up to 60% capability in the future. So that's one problem. The other problem is, NIF fires around once every 3 hours, so once every 10,000 seconds. To do energy, power production, you have to run around 10 times a second. So that's the challenge. How do you go from once every few hours to 10 times a second? Because we need average power, not just energy. Well, this is what it would look like. This is actually a concept of a power plant. And what you have is these targets flying in. Now they fly in, of course, a lot faster. Then the laser hits them, right? And then those neutrons come out. And those neutrons go into this salt blanket. And this salt blanket is flowing by. It actually flows very slowly, a few centimeters a second. And salt is good because it absorbs neutrons. And when it absorbs them, they get hot. The salt gets hot and becomes liquefied. And it has really good heat capacity, so you can use that in the heat exchanger to make steam. If you don't want to make steam, you can heat up carbon dioxide or helium and get better control. So that's that's the basic idea. Some people say, well, what does it really look like? That's how fast, that's 10 hertz. Okay, so anyway, some people say you can't, there's no way to do that. So, when I say 10 hertz, I go multiply by 60, and that's 600 RPM. So how many people are used to 600 RPM devices? Whoa. That's always a bad sign. That's always so how many people are used to 600 RPM devices? So anytime you turn on your car, it's idling at around 600 RPM. So I don't think that. And before I got to this program, I never worked on a laser that worked at less than 10 kilohertz. So I wasn't put off by that. But that's not really the issue. The real issue is not the rep rate. It's managing that much power. And, Dr. Beyer and others at Stanford have been leaders in this field. Diode pump lasers, solid state lasers. Many students here, we're at Northrop Grumman right now. We're showing 100 kilowatt apertures. So this is work that is coming along in any case. So I don't think that's the issue. But there's other things you could do that are even more interesting with those neutrons instead of heating up salt. But I want to talk about this. This is not a target, even though it looks like it. This is the target chamber. This is the way laser people draw some complicated lasers. And then here's a fusion target, which is fired in. When you look at those neutrons coming off, and there are really a lot of them, you get 10 to the 19th per shot. So 10 hertz, you're doing 10 to the 20th neutrons per second. If you think of that in moles, you're getting sort of moles of neutron, a mole of neutron in an hour or so. You could do things than just heat up salt, right? You could, put a little lithium in it. If you do the lithium, you could make, you could capture those neutrons with lithium and make tritium. So you can make your own fusion fuel. So it would not only heat up the salt, but you can make your own fusion fuel so you don't have to make fuel anymore. Now, that's a nice idea. So it's self-perpetual. It's a perpetuating fuel-making machine. It doesn't take away. Or you could do other things. You could say, well, why don't I put some depleted uranium in here? Just a small amount. Really subcritical, K effective of 0.7, way, way away from critical. Now you could get a gain of 4 to 10 with that. So now you could get, a lot more energy out than you want. It's actually even more interesting. Why don't you put something like depleted uranium in, right? Or uranium, or thorium. It doesn't matter. I just want to say this. I think people have to get into this. Right now, when you have a fission reactor, you use about 1% of the energy before it poisons itself. And when it poisons itself, it stops. You have to refuel it, and that's what nuclear waste is, right? And the reason it stops is because it starts making it makes a neutron hog, and it starts absorbing its own neutrons, and it doesn't keep fissioning. So that's how you get this waste. But when you look at if you could burn it down, a ton of uranium or thorium, or plutonium, whatever you like, any one of those fissile materials. Does everyone know how big a ton of those things are? It's about a cubic foot. Is worth a gigawatt year of electricity. I think we should consider that. If you go to Moss Landing on the way to the aquarium, right, that's a 500 megawatt natural gas machine, right? So that means you get 2 years of that much of electricity per cubic foot if you could burn it down to a crisp. What's so great about life, right? You have this point source of neutrons here. You have this blanket that's around 60 centimeters thick. If you put these little balls of depleted uranium or something like that in them, they're smaller than golf balls. You could burn that down to 90%, 99%, whatever you like, and get all the energy out of it. And what's great about that, you now get rid of the whole idea of the whole story of waste changes tremendously. You got to be very careful. It isn't that there isn't any mass left when we burn it down, even though if you weigh it, you sort of lose 300 grams per ton because that's MC squared. You would actually be able to weigh it. But it's now you get around 20 times more energy out per mass in. And what you do is have changed the isotopic mix tremendously, so it has a shorter lifetime on average. There's another thing that, when you go over to the Hoover Institution and you talk to Secretary Schultz or, Professor Drell or any of that crowd, or Kissinger, who are into the zero option, let's get rid of weapons altogether. They say, why don't we just take all of the weapons-grade plutonium we have, and there's a lot of it, and just start making energy out of it. So you could just take, weapons-grade plutonium. I'm not going to say the real number, but just say there's over 100 tons that we can talk about. Go to Wikipedia and just do that. That's 100 gigawatt years. So you could power the United States for a year or so on that. And it's being made in nuclear reactors all the time, right? And so that's an interesting thing. Or you could use spent nuclear fuel instead of going to Yucca Mountain and storing stuff, which President Obama said we're not going to do. You would look at Yucca Mountain. Yucca Mountain as a mine, not as a dump. Because right now, it's waste. And the way I see it, it's a waste of energy. All that energy is sitting in it. So that's one thing you could do. So you could put spent nuclear fuel, natural or depleted uranium, weapons-grade plutonium. You have that little tiny point source of neutrons, size of the diameter of your hair, and just do this. So it's kind of an interesting story. You make your own fusion fuel. You make your own fission fuel. You make lots of electricity, megawatts of electricity, just 1 second, and gigawatts of electricity, and you burn up your waste. So this is an interesting story. Do you want to ask a question? Oh, I'm sorry. I'm very sorry. Thank you. What's really interesting about this process is everything is exothermic except the waste incineration, and even that's exothermic most of the time. So you really are gaining energy in all these processes. Remember, you get a metric ton of material, you get a gigawatt year. So if you had 40 metric tons, which is a small compared to this stage, you could put it in, come back 40 years later, and it would have run the whole time that way. Now, there are some material issues that we have to talk about. One thing that's interesting about this, if we get fusion in 2010, which hopefully we will, or 2011, are there technologies available to do this? And the answer is, we think, and having thought about it a lot, there are no technology issues that aren't 5 to 10 year type challenges that exist now. And it's kind of interesting because most of this stuff is going on anyway. And when you think of big computers like at the labs or now everywhere, it wasn't that everyone said, let's go build a big chip, right? They said, Silicon Valley is making chips. They're faster and faster. Can we hook together 300,000 of them and write code, right? That was the question. I didn't say, let's think of a chip that's 300,000 times more capable. Same here. These kind of diodes are going on. If the United States started building in 2030 and went up to 10 to 12 a year, you could do 50% of the power of the United States carbon-free by 2050. If you look at waste, right now, little known fact, even though we're pretending we're not doing Yucca Mountain at this moment, right now the energy we're using, we're going to need 15 Yucca Mountains or something equivalent in the next, just one second, in the next century. With life, if you did it, you wouldn't need any. We think, I'm going to just skip this for a time. We think that, and Bob and I have talked about this, we've talked with a lot of people about this, 2020 to 2025 is the time scale of this problem, if there's a will to do it. And it's kind of an interesting time period. It gets into, when you talk to the utilities, which we've had a lot of conversation with, the fleet of power generation that's in the United States is going to turn over in 2025 to 2035. So there's a lot of things that are coming to their end of life, 50 to 75-year lifetimes in that period of time. What is it they're going to be replaced with? Maybe this could fit into that. If you look at the amount of fuel we have, if we're getting the pure fusion one where we have infinite amount of fuel, if you did the fusion-fission hybrids, there's right now just laying around, if you never put a shovel in the ground, if you never enriched again, if you didn't reprocess anything, so to take all the issues of proliferation out, there's around $1,000 trillion of energy at today's prices ready to be used. And we call these BUs, buyouts, or So this is the stimulus packages 1,000 times, one a year. There's a huge amount of energy. And by the way, we're spending around $1 trillion a year in energy in the United States or so. So it's kind of an interesting number. It's not a light water reactor. It's not critical. It's deeply subcritical and cannot go critical. I want to just say this. It's on 10 picoseconds at a time. If you go over that, it's on 3 times 10 to the 8th shots per year. It's on for 3 milliseconds a year, which is, to me, an interesting number. And so it's almost never on, but when it's on, it's doing what it has to. And it's a way that you can go either to fusion-fission systems, pure fusion systems. It's a way to get electrons on the grid, we think, in the next 15 or so years, that sort of meets a lot of the demands that we look at as scientists, engineers, social scientists, and the like for our planet. This is what I'm thinking about a lot. I think it's an interesting thing. We've briefed it a lot of people, policymakers, technology people, scientists. Seems to hold together. But it's an interesting problem, and this is what I'd like to do with the rest of my career. So, having said that, we think it's a very interesting idea. I'm very interested in your reaction to this. So thank you very much.
Well, I'll start off. There are a number of questions. One number that I'm curious about, you talked about the megajoule optical pulse. What's the wall plug energy that went in? I'm talking about the efficiency of your laser to make the megajoule pulse.
So a NIF, which is around 1% efficient, it's running around 100 megajoules. With the lasers that we've built in the lab, Bob has built in others, you can see around 12 to 15% efficient.
So when you quote the gain, I mean the question is, for example, when you were sort of comparing it to ITER, you got to use fair comparison cycles in terms of what you're talking about their energy, and you should use your wall plug power, not the optical power. I mean that's a
Well, this is if you want to go through that, we have a full analysis of it, and again, if you look at this, if you look at the fusion gain times the fission gain, the efficiency of the laser, efficiency of the power cycle, if you get that combination to be greater than 10 or so, that means 90% of the power goes out online, 10% is running the plant. And that we have done that, of course, and we have very detailed economic models of this also.
The second question, and then I will not monopolize this, has to do with, you said this is proliferation resistant or reduces proliferation risk, but having the fissile materials, the weapons grade uranium, as part of an energy economy, and having these materials transported around to these sites is actually part of the proliferation risk. So
actually, so that's a really interesting question. If you do pure fusion, there's no proliferation. If you do what the French are doing or the Japanese doing, which is reprocessing, which the United States is not doing, it is a purely proliferation problem because you do once you let a chemist get a hold of that stuff, they have this. The issue would be here for these kind of materials, you would go to Pantex or other places, build a plant, not transport it, just burn it and get rid of it. So once you put it into the machine, it's not touched again. So I think it's at every second that it runs, every tenth of a second that it runs, you would have less of these materials. So I think when we looked at it, we've had it analyzed by IAEA, it's pretty good at this. By the way, nothing is perfectly proliferation resistant, so I just want to say you would not break out using this technology.
So you're not a great fan of ITER, but do you think there's anything that can come out of it? What do you think?
I am a fan of ITER. I am on the management advisory committee. I think I'm a fan of fusion energy altogether, and I think that there's a lot of good that can come out of it. I think that the world faces a huge energy problem, and we should approach all the possibilities that we can. I do think that the ITER project is a very difficult socio-political event. Having been there in Cadarache many times, it's multinational. It's a very difficult issue, and I work with them and wish them the best. So I'm not a non-fan. I am a fan.
I was curious, how far down the binding energy curve do you go if you blanket this thing in uranium or plutonium? How far do you put that, get it close to, I guess, iron to the bottom?
Actually, it's an interesting question when you're doing this stuff. We call it lithium. You make a lot of stuff, and you don't get to iron, but you make many elements. And if you would really want that, we have some papers on that. We could show it to you.
I have two questions. The first is, you mentioned that we could have this accomplished, quote, if we have the will, and I was curious what you meant by that. And the second question is, I know that the University of Rochester has their Omega laser coming on, and it's supposed to not be the most powerful, not the biggest, but more powerful in terms of watts. And I was wondering if there are any results from that you're looking forward to finding out.
Okay, so the first question, let me go in reverse order. The Omega laser at University of Rochester is a 30 kilojoule laser, so it's around 1/80th or so of what NEF is, but they recently put in what's called petawatt lasers, and these are short pulse lasers. So you take these nanosecond pulses and make them picoseconds, and that way you get powers of like 10 to the 15th watts or petawatts. And there are approaches to fusion called fast ignition. The way we do it right now is sort of a diesel engine. You just crush this fuel until it lights, right? But there's another way called fast ignition that was actually invented at Livermore, where you start to crush it, and just like a spark plug, you put a very short pulse in on the side and start a burn. And there's a lot of research in doing that. And so actually, NIF will have actually a very powerful petawatt capability. Right now, Omega does. In Osaka, they have one, and also they're building one at LMJ in France and in AWE in the Great Britain. So that's work that's going on. Also, University of Texas has one too. Okay, the other answer, the other question was, the will versus the way, right? As you grow up in students, you'll find out a lot of times that you have great ideas, but that doesn't mean you get to follow them all out, because you have to get them funded. A lot of people have to agree to do them, especially these kind of big things. And you have to get a consensus community together. You have to get work with Congress. You have to work with industry. You have to pull off the social part of science to make these things happen. So when I talk about the will, I think we think as technologists and scientists we have the way to do it, but that doesn't mean that you necessarily succeed in doing this. NIF, as I say, these big kind of projects are social events, occasionally interrupted by science and technology, right? And that's what I've learned over the last 10 years. So that's what I meant.
Steve?
Yeah, of course, the answer to the other question is costs matter relative to the alternatives, but let's assume that we're still in the exploration stage. As a guy who was a victim of your 50-year joke, because I left Fusion as a postdoc in '71, and when I remember asking a question, so what are the kinds of materials that we use to collect all these large neutron fluxes? And what happens to those materials? How sustainable are they? And do they become a risk themselves afterward, which would affect costs? And I wonder now in the past 45 years what we've learned about that.
Okay, so the question, this is a really important question. If you look at this, this is 5 meters in diameter, right? And the question is, you have this wall, right? And these neutrons are streaming through this wall. Once they get into the salt, there's not really too much issue, right? But this wall is taking a beating, right? And neutrons tend to get into most materials. They embed, they displace atoms. If you sort of get somewhere, some materials, 25 displacements per atom, the thing called embrittles, right? It gets very brittle, and then you sort of have a situation that can start breaking up, leaking, all kinds of junk. Over the last 40 years, people have done a lot of work. This is a huge scientific activity. There's these types of steels now, ODS steels, that can take 150 to 200. There's new ideas using silicon carbide and other that might be much more than that. But this is an active work in both the fusion and the fission communities, because this is one of the reasons why reactors last a lot longer than they originally thought. People have done a lot of work, and you can also anneal them in place. In terms of, what's the radioactivity of it, ODS steels last longer because you take out the bad actors in terms of things that get radioactive. So we get down to is 30-year lifetime radioactivity in those things. That's the general idea. As for cost, we have looked at the cost of this pretty carefully. There's always the thing, if it fuses, if we get ignition, then, right? We haven't gotten ignition yet. We have a lot of confidence, and a lot of people do, that we will. If you assume that it works, then the costs are really kind of interesting, because when you look at power plants, mainly what you're buying is boilers, and steam generators and electrical generators. So there's a lot. 2/3 of the money is there. So that damn laser, right? How much does that laser cost? Is really the interesting thing. And we think that the cost of that is now projected to be low enough that it will be cost competitive. Of course, economic models, and hopefully someone will figure it out, of the cost of carbon are not really understood. So when people are doing this stuff, Wall Street looks at it very differently than I think at this moment, than I think we will. Whether there be taxes on carbon, how will that affect this economy is not well known at this point.
Back to technology, I had a question regarding the lasers. If you have in mind a reactor and thinking the development that
An engine.
Sorry?
An engine.
Engine, right. And you think of the development that you require to come up with your current lasers. Do you, I mean, you look quite confident that you will be able to produce the lasers you need for your engine, but do you really require just an incremental development of current technology, or is more a breakthrough we're talking about?
Okay, so just to say this, and again, this has been going on for a long time. While we've been doing this, the average power community has been hard at work, including all over this valley in this institution. You know, there's a huge amount of work going on. So, you know, and I would defer to Bob also on this, but we have shown at Livermore the ability to do 10 hertz short pulse lasers with the technologies to get high efficiency and run them for millions of pulses. So that is not the question. The question you should ask, but how much does it cost? And what's the capital cost of a watt of average power? And the answer is it comes down to these diodes and how you package them, right? And right now, it used to be until a couple of years ago that diodes were so dominant in the cost that the cost of packaging and power supplies didn't matter. You know, you were just killed by that. In the last couple of years, that has fallen off. It's amazing, you know, has just dropped off the table. So now we're down to the issues of packaging, mass production packaging, and power supplies. And I think the community is pretty confident in the next few years that's going to be resolved. So I don't think it takes a breakthrough. I think it takes things that happen in this valley all the time and are happening.
Do you have any predicted minimum sizes for fusion power plants for construction times? And do you think that delivered fusion electricity will be cheaper than delivered distributed solar?
I think these are really good questions. You know, what is the minimum size of a plant? Well, the minimum size of, you know, fusion plants like to be big. It's hard to believe, but, you know, they like to be gigawatt scale. And there's a lot of interest in getting lower power ones for some people. I will now speak for myself. The future of our species is megacities, right? Megacities are growing faster than the population is. So I don't know why people want to do that, but nevertheless, we sort of see what people are building around the world are, except for natural gas, or gigawatt, 1.5 gigawatt systems. And that's the market we're aiming for, and it sort of fits into that market kind of nicely, right? In terms of how long it would take to build, NIF took 10 years to build, from groundbreaking to finish. And let me tell you, it was a first of its kind. There was a lot to learn along the way. And, you know, we had to facilitize glass manufacturing, all kinds of stuff that never had to be done. We think if we had to build the next one, it would take around 3.5 years. And, you know, so I would think that the first high average power system is another 7 to 10 year problem, you know, getting all that technology in place. And then it would be, looks pretty simple facilities. And our view of facilities of the future, there'll be about 1/5 the volume of NIF.
Is NIF being used to conduct experiments similar to what's being done in the Large Hadron Collider?
The question is NIF being used to do experiments similar to being done in the Large Hadron Collider? The answer is no. You know, the Large Hadron Collider is sort of going back to 10 to the minus 16, 20th seconds. You know, it's a really different world than we're living in. This is not high energy physics. This is high energy density physics, where you get a lot of energy into a small place. Now, it is true when people are looking at nuclear synthesis and things like that on the NIF, which would happen fairly early in the universe, but it's not in any way competing or doing the same kind of work.
What is the temperature regime for these containing structures?
Yeah, this structure right here, this salt we want to run, you know, right now this one is designed to run around 750 C, and we really would like to run it hotter. If you make it a pure fusion machine, you run it at 1100. If you make it a fusion fission machine, then if you have these trisol fuel pellets, they don't like to really get much over 750 degrees with the approved fission fuel, even though we have ideas to do more. The wall is running at around 900 degrees.
Please join me in thanking Dr. Rosa.
Thank you so much. You know, if you ever want to come over to the lab and see this, just give us a call. We'll arrange it. You'll love it.
For more, please visit us at stanford.edu.